Okay, welcome to this lesson recap on binary arithmetic, binary, Daenery, hexadecimal, and negative binary numbers. First question we're doing is converting this binary number here into Daenery. And to be able to do that kind of a question, what we'll be doing is writing the grid. So this is a unsigned binary bit because the one over here is positive. And then what we want to do is write down all these values underneath. So we'll do that super quick now. And then to get our answer correct, every time it's a 1, we want to total up those numbers until we get the total. So we'll be totaling 128 plus 64. We won't add 32 because it's a 0, plus 8, plus 2, plus 1, and that gets our number. This is where I show that I can't do even basic arithmetic correctly. Hopefully not. We've got 2 plus 8 will make us 10, 18, 22, 23. If I've got this wrong and you're at home thinking, you numpty, my apologies. 6 plus 2 is 8, plus another 2 is 10, carry the 1, and then 203. For the next one, it's convert the decimal number 191 into an 8-bit binary. So this time we're going from Daenery into binary, and we'll be doing the grid again. I'm going to be a bit lazy and steal my old one. And then to make this number, to convert 191, let's just zoom in there a little bit. What we want to do is we want to move through these binary bits and see how we store it. So we've got 191. And the question we want to ask is, can we fit 128 into 191? Answer, it'd be yes. And so we write down a 1. Because we've now stored that 128, we have to do 191 take away 191 take away 128. And so if we're making 163, it means that that will be a 0, but then to make up all of this must add up to 63 by definition. So we can just go along and be 0, and then to make 63, we'll need all of these to be on to make that number. Beautiful. Okay, so these are doing the same sort of skills, but we have an opportunity to practice. This one's doing exactly the same thing. We're going to draw the grid, and for this one here, we're going to convert that to hexadecimal, which is something we've not done today so far. So we'll do the grid for binary first. Okay, and now we're trying to put 132 into binary. So we've got 132, and the question we're going to ask is, does 128 fit into 132? And it will be yes. Let's write down 1, and then we'll need to take away 128, leaving us with 4, hopefully, as long as my maths holds up. And as we go along, we'll say, can 64 fit into 4? No, 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 no. And of course, because it's binary, we'll record that as zeros. When we get to 4, it will fit in, leaving us with nothing. And there we go. Now, for the hexadecimal question, what we want to say is we want to recognize that one hexadecimal digit is worth exactly 4 binary bits, or a nibble. And that's deliberate. A hexadecimal exists as shorthand for binary, so that for a byte, instead of having to write out 8 ones and zeros, we can write down 2 hexadecimal digits. So what we do is we'll just split them into 2 nibbles. That was not helpful. I've literally just cut off one bit there, so my apologies. So we're going to do 1, 0, 1, 1, and then 0, 1, 0, 1. And then we can identify what those values are going to be as 2 separate nibbles. So this nibble on the left is 8 plus 2, that will be 10, plus 1 will be 11. But of course, when we get to 10, we make use of letters. So 10 will be A, and B would be 11. So that's B. And on the right, we've got 4 and 1, that'll be 5. So that's B5. Okay, for these questions, we've got hexadecimal converted to Daenery. For the first question, we've got A3, and we need to convert to Daenery. And therefore, what we want to do is this time we do the grid, but we'll do the units for hexadecimal. So those will be lots of 1s and lots of 16s. Typically, you wouldn't go to the next units of 256s because hexadecimal is typically expressed in groups of 2. And anyway, so for this one here, we'll have A lots of 16 and 3 lots of 1. What we have to recognize, and the trick to this question, is that A in hexadecimal is 10. So what we'll do is we'll say it's 10 and then times, and we want to times it by this 16. Just like you would do in binary or Daenery, these are the units and these are how many of the units. So 10 times 16. And then this is a bit pedantic of me, plus 3 lots of 1. Now obviously we could just say 3, but I'm kind of being a bit pedantic to try and make us remember that that's what's happening, that we're timesing by each other. So 10 lots of 16, well, that will give us 160 plus 3, so it gives us the answer of 163, hopefully. Convert the number 3e into a decimal or Daenery number. Typically Daenery is the one they use, so I don't know why we've done this. It's the same question, isn't it, effectively? So let's quickly do that. So we've got lots of 16s, lots of 1s. We write again the 3 under the 16. This time we're doing an e under the 1. We're doing 3 lots of 16. But this time the trick is that we have e. And we have to remember what e means in hexadecimal. Well, the way to do it is you can say, take the time, A is 10, B is 11, C is 12, D is 13, and E is 14. Or alternatively, you can say F is 15, work back 1, E is 14. So that was 14 for E. And again, I'm being a bit pedantic, times by 1. So therefore, when we break it down, 3 lots of 16 is 48, I believe, plus 14. 48 plus 14 is 62. No. Okay, this is yet more practice of converting hex into Daenery. Remember again, these are all exam questions, so I guess it indicates there must be a lot of questions of this way around. So maybe this is something we definitely need to be ready for. For the second question, though, it's converting Daenery back into hex. So we've got 2 sort of different challenges. So remember again, if we're doing hex, we'll do the units. 1s and 16s, we write down the 6, 2 underneath there, and then we'll do the sort of little multiplication. So 6 lots of 16 plus 2 lots of 1. There we go. So 6 lots of 16s. Well, what I would always do is 5 lots of 16s first of all, giving us 80. Add another 16, that would be 96. Remember, you're not allowed calculators in the exam, so make sure you sort of have some kind of shorthand arithmetic. But you can take your time, you don't have to do it in one go. Plus 2, and I believe, oops, I have to keep to the color scheme, otherwise everything will collapse. Equals 98. There we go. And then we have to do it the other way around. So now 62 is actually a Daenery number. We have to convert that into hex. So I'll write out the grid in hex, and we'll do something very similar that we did for binary. So I've got my number I want to make, which is 62. And the first question, before in binary we said, does the number fit in? And now it's not just a question, does it fit in? How many times does it fit in? So we got 2 lots of 16s, 32. 4 lots of 16s would be 64, and that's too far. In fact, we do have this exact number. Anyway, whatever. So it's going to be 3 lots of 16. It's going to give us 48. So now that we've actually stored 48 of it, we have to do that calculation, leaving us with 14. And if we remember in hexadecimal, as soon as we get to 10, we have to use letters. 10 is A, 11 is B, 12 is C, 13 is D, and 14 is E. So the answer would be, I've written it backwards. Can be a bit dyslexic sometimes. So it's 3E. Okay then, so we're doing some binary arithmetic. And for binary arithmetic, we've actually got 2 different length numbers here. This one we've got a byte, and this one we've got 6 bits, or a nibble and a half, or 3/4 of a byte. And to answer the number, we need to start starting from the right or starting from the left. Oh, excellent. So we start on the right. And if you remember, the deal is going to be 0 and 1 is going to give us 1. The deal with 1 and 1 is it's going to give us 2. And we cannot store the number 2 in binary. So instead of writing down 2, we write down 1 over here because we're carrying 2 into the... That's 1 signifies a 2 in the next column. Because we've moved 2 over, we now have 0. Because we had 1 and 1 is 2. We carried the 2 over, leaves us with 0 left. For the next one here, we've got 1 and 1 and 1. Well, that would make 3. And being as that we can't store anything more than 1, we simply cannot store 3. So what we'll do is we'll carry 2 over here, and we'll signify that by writing a 1. 3 take away 2. I believe that leaves us with 1. We've got 0, 0, and 1. Well, that's 1. We've got 1 and 0. That's 1. 1 and 1 is going to give us 2. So what we'll do is we'll carry it over here, leaving us with 0, 1, 1. Okay, we're doing another question here of binary arithmetic. And we start on the right, we start on the left. There you go. So we start on the right, and we've got 0 and 0. Well, that's going to make 0. And then we've got 1 and 1. Now, clearly that's going to make 2, which we can't express, as we said before. So what we'll do is we'll carry the 2 over here, leaving us with 0. 0, 1, and 1 is going to give us 2 again, which we can't deal with. So we carry 1 over here, leaving us with 0. 1, 0, and 1 is going to leave us with 2, which we can't deal with. And 0, carry the 1. Bit of repetition here. 0, 1, and 1. Well, that's going to leave us with 2, which we can't deal with. So we carry it over here, leave us with 0. 1, 0, and 1 is going to leave us with 2, which we can't deal with. So we're going to have to carry it, leaving 0 over here. 1, 0, and 1, which you can't deal with. So I'm going to have to carry it over here, leaving with 0 left. 0, 1, and 1. Hey, guess what? It's going to leave us with 2, which you can't deal with. So we're going to carry it over here, leaving us with 0. And then that is what? Overflow. Because what we're saying right now, according to our sum, is if we add these two values, this value and this value, the total of that is 0. Hey, does that seem likely? No. Because what happened, though, is that without having a additional byte or bit, to carry it, to hold that value, we're going to lose that. So if you think about it, these must be two numbers that make 256. If we had the 1 there, it would make 256. But if we don't have it, suddenly it's become 0, which is clearly not correct. So they identify the problem that has been created. The problem that has been created is that there has been an overflow error, and the way we solve the overflow error is by having an additional bit or byte. Okay, a bit of DIY questions here, looking at sine magnitude and 2's complement, which are the two different ways we can represent a negative number, and as clearly expressed here in a byte's worth, otherwise known as 8 bits. So if we're going to do negative 14 as a sine magnitude, what we'll do is we'll have the first and most significant bit representing plus or minus. Then we'll have 64, 32, 16, 8, 4, 2, and 1. And what we'll do is we'll just make 14. So I'll do that. So that'll be one lot of 8, one lot of 4 gets us to 12, one lot of 2, and then all the rest will be 0. Okay? So that would mean that it's 14. If we want it to be positive on sine magnitude, we'd make that 0. But if we want it to be negative, we'd have to make the most significant bit 1. So that's how you do negative 14 in sine magnitude. 2's complement, which is the one we're going to generally be using because it allows us to do arithmetic operations on it, as well as subtraction, is going to be a little bit more involved. We'll do the grid again, but now when I go 1, 2, 4, 8, 16, when I get to the end, on the most significant bit, what you want to do is make it negative. So it'll be negative 128. And then we follow the recipe. If you remember, the recipe was that we made positive 14. So that would be none of those, one of that, one of that, one of that, and one of that. That's making positive 14. And then the next bit of the recipe is that you flip. So you flip all the bits. Everywhere it's 0, it becomes 1. Everywhere it's 1, it becomes 0. So we'll do that. So we'll go 1, 1, 1, 1, 0, 0, 0. And that's actually technically something called 1's complement, but we're just 1 off. We have to add 1 to get the number we want. So we have to actually add 1, so plus 1. So plus. Now, here's somewhere we can go a bit wrong, is I actually want to add this number to this number. This is no longer relevant. And in fact, to do that, I think what I might do, I've stiffed myself here because I've run out of space. I'm just going to highlight the two ones we're actually adding together. So it's this one and this one. And then when we're adding numbers, we start on the right. So 1 and 1 is going to make 2, which we can't store. So we make 0. Oops. We make 0, carry the 1. So I'll put it in there. And then that's it. The rest, we can just copy down that top number. So 0, 0, 1, 1, 1, 1. Apologies for running out of space. That's really not ideal. So negative 128 plus 64 makes negative 64, plus 32 makes negative 32, plus 16 makes negative 16, plus 2 makes negative 14, which is the number we're trying to make. Okay, I'm going to have another go at doing 113. In your book, copy and paste the original one you had. That's a typical thing you can just do in a book, right? And then you want to make your number, which is negative 113. So in 2's complement, we first of all make positive 113. Oh, I have to work on my adding. So that would be 64 and 32 is a 96. Plus 16 would be 112. Right, and then like that. Yes, and then we want to flip. And then we want to add 1. So truthfully, I could have just changed the last one to a 1, made my life easier, but you know, why would I want to do that? So, and then we add those two together, and there we go. Negative 113 in what? In 2's complement. Beautiful.